All right. I'd like to get started. First, can anyone hear me?
Yes.
Good. Thank you very much. All right. Today, I want to talk about the transition between running in user code, running programs in user code, and executing in the kernel. And this is the transition that has to happen whenever a program makes a system call, or if it experiences a fault like a page fault or divide by zero, or if a device decides to interrupt and needs to be served by a kernel device driver. There's a lot of careful design and sort of important details that go into how these traps from user to kernel happen. And the details are pretty important for enforcing isolation, security, and also for performance. There's many programs that transition to the kernel a lot, either due to system calls or page faults. And it can be super important that the trap mechanism is as streamlined as possible. All right, so the starting situation is pretty familiar. We have our user program. I'll use the shell as an example. It's running up in user space, and we have the kernel. And what the shell would like to do is make a system call into the kernel. And I'm going to use write. I'm going to use this shell writing its prompt, the very first write that happens after you boot x86. I'm going to use the shell trying to make the write system call as an example. And so we need to figure out how to actually get execution to transfer from running in the shell in the user space with user privileges to running in the kernel with supervisor privileges. The state of the hardware is going to be very important, because a lot of what we're doing is kind of changing the hardware state from state appropriate for running user code to state appropriate for running kernel code. The state that we care about, now, the biggest state is maybe the 32 user registers. As you remember this from Monday's discussion, we have all the user registers, things like A0 and A1. RISC-V has a whole lot of these, 32 in total. And we can expect user code to use all of them. Right? It's going to get the highest performance if it uses all of them. Many of them have special purposes, a few of which we'll see. A particularly interesting one is the stack pointer is actually one of these 32 general purpose registers. Okay, we have these registers, including a stack pointer. There's a separate program counter register in the hardware. There's the current mode, either supervisor or user, and of course it's user mode when we're executing up in the shell. And then there's a bunch of registers, special registers that control how the CPU works. Like there's the SATP register that contains a pointer to the page table. And it'll turn out there's a couple of others that are super important for this discussion. There's this STVEC, which is the address of the instruction that should handle traps in the kernel. There's a register called SCPC for saving the program counter during a trap. And we'll see there's another one called scratch, which is also very important. So this is the state of the running machine at the time of the system call. And we actually need to change a bunch of this state or do things to this state as part of getting into the kernel and setting ourselves up to run just ordinary C functions in the kernel. Certainly at the instant of the trap, all the state of the CPU is set up to run user code, not kernel code. So the things that are going to need to happen is kind of a preview of what I'll talk about. One is that we need to save all 32 registers because we want to resume the user code transparently, particularly if there's a device interrupt, which the user code isn't expecting. And we want to be able to have the kernel serve the interrupt and then resume the user code without it ever noticing any difference. And that means that these 32 registers can't be disturbed by the kernel, and since the kernel needs to use the registers, it has to save them all somewhere first. So these need to be saved. The program counter also needs to be saved somewhere because we need to, it's almost like a user register. So we need to continue executing the user program where it left off. We need to switch the mode to supervisor mode because we need to use various privileges in the kernel. This page table pointer is currently pointing towards the user page table, which only contains just the mappings that user programs need. plus 1 or 2 more, as we'll see, but the user page table does not contain the mappings for the bulk of the kernel data. So we need to switch page tables before we can run most kernel code. We need to switch the stack pointer to point to a stack that's in the kernel somewhere, because we need a stack to call C functions on. And finally, we need to jump into, once we've set all this up and switched all these resources to be appropriate for use in the kernel, we need to jump to kernel C code. And once we're in C code, life is much more sort of business as usual. We're just running a C program in this kernel. And so for today, at least, we'll talk about what the kernel does in the C code later. But today, the discussion is really how to get from user space into the kernel, into a position where we can run C code in the kernel. There's a couple of high-level goals that constrain our design options for this. One is that for security and isolation, we really don't want to let the user code interfere with this user kernel transition in a way that could be damaging to security. And so that means that the sort of hardware and kernel mechanisms that are involved in traps really can't count on anything from user space. We can't assume anything about these registers. They could be just filled with terribly malicious values. So basically, the XV6 trap handler doesn't really even look at these registers. It just saves them away. So we're going to want to be careful to preserve isolation during this trap mechanism against intentionally malicious user code. And the other thing that's important is that we want to be transparent to user code. We'd like to be able to take the trap and do our business in the kernel and resume the user code without it ever having to notice that anything funny happened. And that's just to make it easier to write user code. Something to note, we care about isolation and security here. Today, we're just going to talk about the sort of aspect of security that involves getting into the kernel. But of course, the system call implementations, the actual write implementation in the kernel, also everything in the kernel has to be careful, has to be written carefully and securely also. So even if this transition into the kernel is perfectly secure, the whole rest of the kernel has to be written securely and sort of mindful that user code may be trying to trick it. A particularly important thing I want to talk about is what it is that the mode flag controls. This mode is either user or supervisor. Of course, it's user when we're up in user space, and the mode flag is set to supervisor when we're executing in the kernel. But it's important to know exactly what privileges we gain by changing the mode from user to supervisor. And it turns out these extra privileges are fairly restrictive. That is, what you can do in supervisor mode that you couldn't do in user mode is not maybe as privileged as you might think. So this is supervisor mode, like exactly what it controls. One thing it does is you can now read and write the control registers. And that is, if you're in supervisor mode, you can read and write SATP, the page table pointer, this STVEC pointer, which controls where traps go in the kernel, this register that holds the save program counter during a trap, and this scratch register, plus a few others. So supervisor could read and write these registers, and user code could not. The only other thing supervisor code can do is it can use PTEs that have the PTEU flag set. I don't know if you remember, but there's this PTEU flag, it can be set or not set in each page table entry. A flag that has this, you can use PTEs that don't have the PTEU flag set. If the PTEU flag is set, it means that user code can use that page table entry. If this flag isn't set in the page table entry, it means only supervisor mode can use it. And we'll see that's important in a little bit, but these are really the only things that supervisor mode can do. It can't do anything else. In particular, for example, supervisor mode code can't just read and write arbitrary addresses, say physical addresses. No, supervisor mode is forced to go through the page table, just like any other code. If a virtual address isn't in the current page table pointed to by SATP, or if it has the PTEU bit flag set, which means it's a user PTE, then supervisor mode code cannot use that address. So we're even in supervisor mode, we're restricted to whatever virtual addresses were set up in the current page table. And that's it. So we're just allowed to do these things. So, we'll see. There's a significant constraint on what the trap code can do when we're entering the kernel. Can't do just anything. I'm going to preview a bit. I'm going to spend most of this lecture in GDB actually tracing through the execution of a trap entry into the kernel and return. There's going to be a lot of details. In order to maybe sort of help you see ahead to what's coming, we're going to be tracing the shell's call to write, which from the shell's point of view is just a C function call as part of the shell. In fact, write makes this, might issues a system call by issuing the eCall instruction, which switches into the kernel and switches to supervisor mode. Where that goes immediately, that is the very first instruction that's executed in the kernel in supervisor mode, is in a function written in assembler called uservec. And this is in the part of the trampoline in trampoline.s in the kernel source. So the very first code that's executed is this uservec assembler function. And next, that assembler function jumps into C code, in particular a function called usertrap in trap.c. And now we're getting into C code, so things are much easier to understand. Usertrap sees, we're executing a system call, and it calls a function called syscall, which looks up the system call number in a table and calls the particular function inside the kernel that implements that system call. And for us, it's going to be write. And write does its business. It happens to, arrange for the whatever bytes were written to appear on the console. And when it's finished, it returns back up to this system call function. And then the system call function, in order to return back to user space, because we want to resume after this eCall, there's a bunch of stuff we'll see that has to happen in order to return to user space. So there's a separate function called user trap ret. It's written in C, it's in trap.c that does the part of this return to user space that's convenient to do in C code. There's some final things that really can only be done in assembly code. And the code for that is written in assembler, and it's again in this trampoline page in a function called userret. So there's some last assembly stuff that has to happen. And then finally, this assembly function issues the machine instruction that returns back in user space and resume execution after the eCall. All right, does anybody want to ask a question? I'm about to switch into looking at stuff with GDB. Any questions about the sort of high level picture? All right, I am going to.
Questions in the.
Sorry,
chat.
I can't.
Let me see. What mode are VM.c functions run in?
VM.c functions, everything in there is a part of the kernel, and it's run in supervisor mode. Yeah. Okay. Somebody asked why these functions are named this way. The naming is a bit of a disaster, and for next year, I'm resolved to make them more rational.
I think the naming question might have referred to the name of the registers in the previous board.
They all start with S for supervisor. Other than that, there's 5 people pick these names. Somebody's asking, don't the VM.c functions access physical memory directly? That's absolutely true. The reason why they're allowed to do that, though, is that the kernel carefully sets up direct mappings in the page table. There's been many, many PTEs in the page table which cause, whenever the kernel tries to read or write a physical address, it actually is a virtual address that's translated by the kernel page table into the physical address that's equal to the virtual address that was issued. So it's like super convenient in the kernel. Once you're using the kernel page table, because the kernel has all these direct mappings. But until we've set up until the trap machinery has switched to the kernel page table, none of those mappings are available. So until the kernel trap code is switched to the kernel page table, we're still using the user page table, which has none of these convenient mappings for physical addresses. Okay.
Can I ask a question?
Please.
I don't know, this is maybe not exactly relevant to what was just said, but the read and write system calls, right? Like those are pretty expensive compared to just a memory store, because you have to actually switch modes and go back and forth. Would it be possible to just like, instead of when you open a file, instead of getting back a file descriptor that you call with a system call, to get a page table mapping, and then you would just write to a certain address that's just mapped to the device, and you can set up the restrictions so that the program can only write to like a file descriptor that it's allowed to, which is allowed to through the virtual page table mapping, instead of jumping to the kernel and back.
Yeah, that's a good observation. And indeed, many operating systems provide this, what's called memory mapped file access, where indeed you map pages that correspond to the file contents into your virtual address, into the user virtual address space, so you can read or write them directly through memory. In fact, you'll be implementing a version of this in the mmap lab in a couple of weeks. And indeed, as you imply, it's a good deal faster for many programs than calling read and write. Okay. I'm gonna switch to the GDB world. All right, at this point, everybody should see my screen share. We're going to watch an XV system call, the shell's write of its initial prompt, make its way through the system. You can see the user code that initiates this in sh.c. And I'm showing that here. It's just making the write system call with this $ prompt. Let me fire up GDB. Excellent. So what actually happens when user code, when the shell calls write is just it's a library function that's part of the, that's linked into the shell. And you can see the source for it in usys.s. So it's this couple of instructions here is the implementation of the write function that the shell is actually calling. And this is a very short function. All it's doing is loading into A7 a number, syswrite, which is just symbolically defined to be 16, that tells the kernel, I want to run the 16th system call, which happens to be write. And then this little function uses the ecall instruction, which is what actually gets the code into the kernel. The kernel does its thing. And then when the kernel's finally done, it returns back into user space to execute the instruction after the ecall, which is that ret that returns back to the shell, returns from that write library function back into the shell. So what I'd like to do in order to show the system call part of this, I'm going to start by putting a breakpoint on that ecall instruction. And we need to know its address, of course, but we can find that out by looking in sh.asm, which the XV6 compilation process produces. And in sh.asm, there's a assembly code with addresses of the instructions for the shell. So I'm going to put a breakpoint on the ecall instruction, which is at address DE6. Excellent. I'm going to actually start XV6 running And I'm hoping to have the system break in the shell just before executing eCall. All right, excellent. We're now, you can see from GDB, we're about to execute that eCall. Let's just check that we are where we think we are. Let's print, we can print the program counter. This is 0xDE6, just what we asked for. We can also print all 32 registers, and some of these values, whatever, we don't know, we don't care what they are, but A0, A1, and A2 are the 3 arguments that the shell passed to write. And so those arguments are file descriptor 2 in A0, the pointer to the buffer of characters that the shell wants to write in A1, and the number of characters it wants to write in A2. And we can convince ourselves that we're looking at the code we think we're looking at by actually printing out the bytes in that buffer that the shell wants to write. And indeed, it's a $ and a space. So we're at the system call that we hope to be at. One thing to notice is that the program counter and the stack pointer are both at low addresses quite close to 0. And that just reinforces our belief that we're still executing in the user address space, where all the addresses are quite small. Once we get into the kernel, you'll see the addresses are, the kernel's actually loaded much, much higher in memory. Okay, the point of the system call is to switch around a lot of state. One of the most important pieces of state that has to get switched and that we have to live with before it's switched is the current page table. Of course, we can look at SATP, but all we get there is the address and physical memory. The page table doesn't actually tell us much about what the mappings are, what the page table looks like. Luckily, there's a way in QEMU to ask it to print the current page table. And if I print Control-A-C, I get into the QEMU monitor or console. And if I then type info-mem, it'll print the complete page table. Now, this is a very small page table. It contains only 6 mappings. Of course, it's the page table for the shell. Shell's a pretty small program. And these 6 mappings are in order: the shell's instructions, the shell's data, an invalid page which acts as the stack a guard page in case the shell tries to use too much stack space. And we can see it's invalid because it doesn't have the U flag set. Over here in this attribute or flag column, these are all the PTE underscore flags. RW and X are just control whether a page can be read or written or executed. The next column is U, and that's whether or not the PTE U flag is set. And user code can only get at PTE entries for which the U flag is set. I don't know what the next column is, I have to admit. And the next column is A for whether the page table entry has ever been used, and D for whether a write has ever been issued for this address. Okay, so we have this tiny page table, and the last 2 page table entries, by the way, are way up at enormous virtual addresses, very close to the top of the virtual address space. And these 2, as you read about in the book, and we'll hear much more about, are the trap frame page and the trampoline page. And as you can see, neither of them has the U bit set. So user code can't get at either of these, can't use either of these addresses. But once we enter supervisor mode, we can get at these 2 pages. All right. One thing to notice about this page table is there's no mappings for anything in the kernel. There's no physical address mappings. There's no mappings for the kernel's data or the kernel's instructions or anything else. So this is except for the last 2, just the very last 2 pages. Now, this is a page table almost entirely dedicated to user execution and is not directly particularly useful for executing the kernel. All right.
What's the A attribute on the page table listing on the top?
I believe this means the page table has ever been, this page table entry has ever been accessed by code. That is, whether it's ever issued an address that refers to this page table entry. And the D is whether the program has ever written, ever done a store through this page table entry. And these are bits that the hardware maintains for the convenience of the operating system. And operating systems more sophisticated than x86 may need to evict pages. If they're running short on physical memory, they may need to write some pages of memory to disk and invalidate the page table entries to free up the physical memory. And many policies you can imagine an operating system using to pick which pages to exist will consult the A bits to see whether this page table entry has ever even been used. And if it hasn't been used or hasn't been used recently, then that's a good candidate for evicting to disk. And the D tells the kernel that, oh, this page has actually been written since it was read from disk. x86 doesn't actually use either of these. All right, other questions? All right, let's execute the, let me just remind us where we are. I'm gonna print out the contents of the write. We're in the write library function in the shell, and the program counter is pointed at the ecall instruction. We're about to execute the ecall instruction. We're still in user space, but we won't be for long. Boom, I executed the ecall instruction. Okay, so first question is, where are we after the ecall? We can look at the program counter. We see it's now, used to be a very low number, DE6, now it's a very high number. In fact, if we look at the program counter as a virtual address, like all addresses that instructions use. And we can look in the page table. Actually, let's just check what the page table is, just to be sure. I'm gonna ask QEMU for info mem again. It's the very same page table. So nothing's changed there. We'll look up our new current program counter there. The program counter is at the right at the beginning of this trampoline page that's mapped way up high in the user memory. So that's where we're executing. We can see the instructions that are there. I'm going to use these are the instructions, the very first instructions that the kernel executes in supervisor mode at the beginning, very beginning of a trap. And through some weirdness in GDB, we've actually already executed the first instruction at the very beginning of this page. And we're about to execute the second instruction. We can look at the registers. I don't know if you remember these register values, but nothing has changed here. These are exactly the same register contents that the user program had. So these are all full of user values. For many of them, or all of them, for all we know, they're the only locations these values exist. So we have to be very careful that we can't actually use any registers at this point without first saving those registers somewhere so we can restore them. Because if the kernel was to use any of these registers at this point, it would overwrite whatever that user value is. And then if we tried to resume the user program, we wouldn't be able to set up its registers with the correct values, and the user program would just do something totally wrong.
Question?
Yes.
Could you return to the instructions panel that you had before? I'm wondering what the CRRW instruction is doing.
The CSRRW. Okay, we'll talk about this in a few minutes. But the answer to your question is that instruction swaps A0 with the contents of the special scratch register. And so yeah. Okay, and this is like super important and basically answers the question, how can this kernel trap code do anything if it can't use any registers? And the answer to that question is that it really has to execute this CSRRW A0 scratch instruction that simultaneously saves A0 in scratch and happens to load scratch into A0. So now the kernel can use A0 for whatever it wants to after this instruction.
Okay, thanks.
Yeah. Okay, so we're currently, this address, this 3FFFFFF000, this last page is the trampoline page, and we're currently executing in the trampoline page, which contains the very first instructions of the kernel's trap handling code. Ecall doesn't switch page tables. That's a very important thing about ecall. And what that means is that these very first instructions have to be present in every user page table. Because since ecall doesn't switch page tables, we need to be executing the first bit of the kernel somewhere in the user page table. And it's this trampoline page, which the kernel carefully maps into every user page table, that gives the kernel a place to execute at the very beginning of a trap when we're still using the user page table. And the way this is controlled is through the STVEC register. This is another privileged register, only writable by the supervisor. And the kernel, before it entered user space, set up the STVEC to point to the place where the kernel wanted traps to go. And so as you can see, the kernel has previously set up this STVEC to this 3FFFFF000 address, which is the beginning of the trampoline page. And it's this STVEC register that its contents is the reason why after the ecall, we ended up executing at this particular place. And finally, I just want to remind you that even though the trampoline and trap frame pages are mapped into the user page table, the user address space, the user code cannot write them because the PTEs for them don't have the PTEU flag. So they're protected against user code. And that's why this trick is, or part of the reason why this trick is safe. I've been sort of telling you and assuming that we're in supervisor mode. I don't know any way of finding out what mode the machine is in directly. But I do observe that the program counter is currently executing in a page, the trampoline page, that doesn't have a PTEU flag set. And that can only happen without a crash if we are in supervisor mode. So I deduce from the lack of a crash and the value of the program counter that we must be in supervisor mode. How we got here, of course, is through ecall. Ecall really just changes three things. First, ecall changes mode from user to supervisor. Second, ecall saves the program counter register in the SEPC register. So we can see the effect of that. I print the program counter. It's certainly no longer the user program counter, even though all the other registers were. It's this value copied from STVEC. And we can also print the saved, it's the supervisor exception program counter is what that stands for. But this is where ecall saves the user program counter. And that has the familiar value DE6, which is the address in user space of the ecall instruction. So we got that one register at least saved away by ecall. And the final thing that ecall does, the third thing it does, is jump to the instruction that STVEC points to. All right. So what needs to happen now? Ecall's done a little bit of work for us, but it turns out we're nowhere near ready to actually execute ordinary C code in the kernel. What has to happen now is we need to save the 32 user register contents so we can later restore them and when we want to resume the user code. We need to switch to the kernel page table because currently we're using the user page table. We need to create a stack or find a stack and set the stack pointer register to point to the kernel stack so we can run C code, which requires a stack. And then we need to actually jump to some sensible place in the C code in the kernel. Now, as an aside, ecall didn't do any of these things for us. But you could have, the hardware could have defined ecall to do much more, many more of these steps for us instead of leaving them to software. And as we'll see, doing them with software is not particularly straightforward. So you should ask yourself why the ecall doesn't do more of the work of getting from user space into the kernel. Why doesn't it save their user registers or switch page table pointers to point to the kernel page table, or automatically set the stack pointer to point to the kernel stack, or jump right to kernel C code, geez, rather than having to go through all this complicated assembly code. And there's actually been machines that have done all of these things in hardware during system calls. The RISC-V doesn't do any of them. The RISC-V, really, the attitude they've taken is that ecall does the absolute minimum that's required that it could possibly do and leave everything else up to software. And the reason for this is because the RISC-V designers want to allow maximum flexibility to the software, the operating system programmers to design the operating system however they like. And so you can imagine ways, XV6 really doesn't use this freedom, but other operating systems do. So some examples of things that are kind of enabled for the software to do because eCall is so simple. Maybe some operating systems can execute some traps, some system calls without switching page tables. The switching page table is expensive. If eCall forces you to do it, that rules out the possibility of very streamlined implementations for some system calls that don't switch page tables. Some operating systems map both user and kernel virtual addresses into a single page table and use the same page table for both user and kernel, and therefore don't even have to switch page tables ever when transitioning between user and kernel. And for them also, if eCall switched page tables, that would just be a waste and slow things down. Maybe in some circumstances, system calls, for example, some registers don't have to be saved. And which ones have to be saved or not sort of depends on the software, the language, and the compiler, but you might be able to save a lot of time by saving fewer than 32 registers. So you don't want eCall to kind of force you. You don't necessarily want eCall to force you to save all the registers. And finally, maybe no stack at all is required for some simple system calls. So again, for operating systems that care a lot about performance, it's good that eCall doesn't force any particular stack policy on you. And again, there's been many clever hardware, software schemes for very streamlined, high performance system calls and traps, just because the performance of this stuff is like super important and people worry about it a lot. Okay, so back to XV6 and then RISC-V. The first thing we need to do is save some registers. We can do hardly anything on the RISC-V without a few registers, without being able to use registers. So what are our options for saving user registers? On some other machine, we might be able to just write the contents of the 32 registers somewhere convenient in physical memory. We can't actually really do that on the RISC-V because supervisor code isn't allowed to directly access physical memory. We can only use what's in the page table. There's not much in the page table. Another possibility that XV6 doesn't do is simply setting the SAT-P to the kernel page table, right? And then we could use all the kernel mappings and use them maybe to help us save the user registers. And that'd be legal. The supervisor can certainly change SAT-P. However, at this point in the trap handler, namely the beginning, we don't even know the address of the kernel page table. And furthermore, the instruction that you execute to change SAT-P require that the address that you're loading into SAT-P come from a register. So to even execute the instruction to change page tables, we need some spare registers in order to put the new page table address in those registers so we can execute the SAT-P modifying instruction. All right, so we really need to save the user registers. There's two parts to the solution for how XV6 does this on the RISC-V. One is, part of the solution is that XV6 into every user address, every user page table maps this trap frame page. And every process has its own trap frame page. And the trap frame page actually contains some interesting, a bunch of different kinds of data, but at this point, the most important data it contains is 32 slots, empty slots in memory in which to save the 32 registers. So the good news right now in the trap handling code is that we have a mapping, we're guaranteed to have a mapping set up by the kernel previously in the user page table that points to a place where that's prepared for us to save this process's user registers. And it's always 3 FFF E000 virtual address. And if you want to see what's there actually in that trap frame, it's what XV6 puts there is defined in proc.h and struct trap frame, which is right here. So you can see what's supposed to go in each slot. And there's 32 slots, named RA, SB, GP, whatever, which are places to save registers. There's also these 5 things at the beginning, which we'll see will come in handy very soon, which are values that the kernel previously placed in these slots in the trap frame. Like, for example, this very first slot in the trap frame contains a pointer to the kernel page table. And this will be the value that we're very soon gonna, the trap handling code's gonna load into SATP. Okay, so half the answer to how to save the registers is that the kernel has conveniently mapped this trap frame into every user page table. The other is this instruction, this scratch register, which we mentioned before. So there's the special scratch register provided by RISC-V for exactly the purpose we're about to use it for. The kernel, before it goes into user space, puts a pointer there to the trap frame. Basically, just puts into SATP this address, just for the convenience of the trap handling code. More importantly, though, there's an instruction in the RISC-V that it's going to allow us to swap any register in scratch, which will save that register as well as load the value of scratch into whatever register we specify. As you can see, if I look at the trampoline code, we're right at the beginning of the trampoline code here. The very first thing it does is this CSRRW instruction. This is the source in this window. Over in this window, we can actually see what GDB sees in the kernel. And we've actually just executed this swap instruction. And it swaps A0 with scratch. In order to see what it did, let's print out A0. A0 is now this 3FFFE000 value, which is a pointer, which is the virtual address of the trap frame, which used to be in scratch, but we just swapped it. And then we can print out what's in scratch. And it's 2, which is the old value of the A0 register. Of course, A0 held the first argument to the write function, which is file descriptor 2, which is what the shell passed. So we've saved away A0, and we have a pointer to the trap frame. And it turns out now that we're well on our way to being able to save the registers. In fact, that's what the very next 30-odd instructions do in this trampoline code. It just systematically executes these SD instructions. These are just 64-bit save, store instructions to store every single register to a different offset in the trap frame. A0, if you recall, now contains, after the swap, contains a pointer to the trap frame that contains the virtual address of this page. And we're just storing each register at a different offset in the trap frame. All these stores are a bit boring, so I think I'm going to skip over them. And let me set a breakpoint a little farther on.
Professor, question?
Yes.
How did the address of the trap frame end up in scratch when we swapped it with A0?
Okay, before the kernel, before it previously transitioned to user space, set scratch to be equal to 3FFFFFE000, the virtual address of the trap frame. So all the time when we were executing in user space in the shell, scratch had this pointer to the trap frame. And then the shell executes ecall, which jumps to the beginning of the trampoline. And the very first instruction in the trampoline is this CSRW instruction, which swaps A0 and the scratch. And so now the old value of the scratch, namely the pointer of the trap frame, is now in A0. Does that answer your question?
And I guess I'm wondering where in the does this happen during the allocation of the process? Like, where does the scratch register live?
Where does this, well, the scratch register itself lives on the CPU. It's a special register in the CPU, and the kernel sets it, it's a little bit involved. The actual place where it's set, or what I'm now showing you on the right here, is the code that the kernel, the last 2 instructions that the kernel executes while returning to user space. And what's happening is that the very last thing it does after the kernel restores all the user registers and is just about ready to return to user space, it actually does another one of these swaps. The kernel has set up A0 to be equal to the trap frame. Scratch still holds the saved user A0 So the kernel does this swap, which ends up with scratch having a pointer to the trap frame and A0 having the saved user A0, and then this sret returns to user space. So you may wonder how A0 ever got to have the value of the address of the trap frame. The answer to that question is that we're now looking in trap.c at this last C function to run on the way out to user space. And the last thing this C function does is calls this function here, whatever this fn is, and the arguments it passes are the trap frame and the user page table. And so in C code, when you call a function, the first argument goes in A0. And that's basically why A0 held a pointer to the trap frame. And this function, its value is set up here to be in that trampoline page towards the end, that code I showed you, this code. Is that a good answer?
Yes, thanks.
Sorry, I also was confused about that. I was not sure. So when you start your process and it's good and running, and then at some point it doesn't equal, I guess, in something, and then when did you call this return function? Because it should have been called before the call, but you didn't return before. I don't know. I don't understand what you call the user trap-ret.
Okay, maybe one answer to this question is that the kernel always, or the machine boots up in the kernel. So when the machine starts, it's in the kernel. Anytime, the only way to get into user space, the very first time or when returning from a system call is in fact to execute this sret instruction. That this sret instruction is the way that the RISC-V defines to transition from supervisor mode into user mode. And so before any user code ever executes, the kernel executes the code I'm showing you here in these two editor buffers that set up all kinds of things like scratch and stvec.
Okay, I see. Thank you.
You're welcome.
I have a question. I'm not sure if we touched on this or if I missed it, but when we call the eCall instruction in the assembly code, what triggers the trampoline code to start? Like, is it the switch of the CPU mode from from user to supervisor, or is it something else?
Okay. So the code we're executing is this eCall. The shell executes it in user space. And eCall does a couple things. The eCall instruction sets the mode to supervisor. And the eCall instruction saves the program counter in EPC, and the eCall instruction sets the program counter equal to the control register called stvec. And stvec is one of the many things which the kernel sets up before entering user space. And so here's stvec. Stvec is just the kernel set it to the beginning of the trampoline page, that is this address here, so that when eCall happens, eCall just copies stvec into the program counter and continues. But now the program counter is executing at this address in the trampoline page.
That clarifies it. Thank you.
Okay.
I also have a question. So some of the registers that are saved in the trap frame should not, are also registers that the user program had access to. Why did we need to use a new region in memory and not use the program stack?
Okay. Well, there's maybe two questions here. One is maybe why do we have to save the registers at all? The reason why the kernel has to save the registers is that the kernel is about to run C code that it overwrites those registers. And if we ever want to resume the user code correctly, we need to resume it with its registers having their original values, as of when the eCall was executed. So we have to save all the registers in the trap frame so that later on we can restore all of their values just before resuming the user code. Maybe the other half of your question is how come they're saved in the trap frame and not on the user stack? The answer to that is that we're not sure the user program even has a stack. Right? There are certainly programming languages that don't have a stack. And the stack pointer doesn't point to anything in particular, or might have value 0. There's also programming languages that, yeah, they have a stack, but it's in like a format that's, some weird format that the kernel doesn't understand. Maybe because the programming language allocates its stack in small blocks from the heap. And the programming language runtime understands how to use these small blocks of memory as a stack, but the kernel has no idea. So if we want to be able to run sort of arbitrary user programs written in lots of different languages, the kernel can't make any assumptions about what parts of user memory it's allowed to exist or valid, or it's allowed to read or write. And so the kernel has to be sort of self-contained in saving and restoring the registers. That's why the kernel saves this stuff in its own memory in the trap frame rather than in user memory.
Okay, makes sense.
Okay. Anything else? Okay, we're still right at the beginning of the code in Trampoline. This code is, unfortunately, we refer to it both as uservec and as the Trampoline code. We barely started executing it. I think I just set a breakpoint in this code after all the registers have been saved. I think I set a breakpoint of this instruction. So we'll continue executing, we'll skip over all these saves of all the user registers to the trap frame. Okay, and now we're executing this load instruction. This load instruction is loading into the stack pointer register. And what it's loading is the value, is the 8th slot in the block of memory pointed to by A0. We remember A0 points to the trap frame, to this virtual address, the second to last page. And the format of the trap page, of the trap frame, here's the format of the trap frame. We've conveniently labeled each field with its offset in bytes. So that means they're loading the 8th, starting at the 8th byte of the trap frame means we're loading the kernel stack pointer. And one of the things the kernel sets up before entering user space is it sets this slot in the trap frame to be equal to this process's kernel stack. So what this instruction here is doing is initializing the stack pointer to point to the top of this process's kernel stack, which is part of what you need to do in order to run user code. All right, so what's left? We're within a few instructions of getting to the end of this Trampoline code. We loaded the stack pointer. So maybe I can print the stack pointer for you. Let's see. Yeah, this is all right, well, this is the kernel's, this process is kernel stack. It's up in high memory because XV6 treats kernel stacks specially so that it can put a guard page under each kernel stack. Okay, so this load into TP, it turns out that because there's no direct way in RISC-V to figure out what core, which of the multiple cores you're running on, XV6 actually keeps the core number called the heart ID in the TP register. And this is used in a bunch of places in the kernel. For example, it's part of the machinery for kernel code to figure out what process is currently running on that core. Okay, and if we execute this, hopefully TP, we're running on core 0. And that makes sense because I've configured QEMU to only give one core to XV6. So we are indeed running on core 0. This next thing is loading the address of, well, actually the load into T0, I think loaded a pointer to the first C function that we're going to execute, which is user trap. So we use that in a few instructions to just jump to the user trap C function. This load into T1 here is loading the address of the kernel page table. So we can print. So we're about to switch page tables. Turns out the this thing in T1 is not actually literally the address of the kernel page table. It's the thing you need to put into SATP, which is has the address of the kernel page table, but shifted around with some extra flag bits set. But as soon as the CSRW instruction executes, we'll switch page tables from the user page table to the kernel page table. And let me just reinforce that by looking at the current page table. You know, right now, we're still executing with this very small user page table. I'm going to run step I to execute the load into SATP. And we'll look again at the kernel page. And now we're in a completely different page table, right? This is the kernel page table. And you can see all these different regions of memory and device control registers and whatnot that the kernel sets up in its own big kernel page table. So we successfully switched page tables now to the kernel page tables. And so we're like in pretty good shape at this point because we have a stack. We have the kernel page table. We can read and write kernel data. We're really pretty much ready to execute C code in the kernel. One puzzle though is how come we didn't just crash? After all, we were executing somewhere in memory and the program counter holds a virtual address. If we switch page tables, why doesn't that just cause some random garbage or nothing at all to be mapped in the new page table underfoot where we were executing? Right? We're not crashing here, we're actually executing these instructions. Any guesses what's going on?
I think it's because, oh, sorry.
Because we're still in the trampoline code and the trampoline is mapped the same virtual address both in user and kernel.
That's absolutely correct. And so I don't know if you remember what was mapped here in the user page table, but this mapping here at the end of the kernel page table is exactly the same mapping in the same place as the trampoline mapping at the end of the user page table. All the other mappings are different, but this mapping is the same. This is the mapping that holds the instructions we were executing. And because it didn't change when we switched page tables, we can actually continue executing and we're still executing the same sequence of instructions and not crashing. And so that's the sort of special thing about the trampoline page. It's mapped both into user page tables and into the kernel page table. And the reason it's called a trampoline page is because you sort of bounce on it on the way from user space to kernel page space. And with the next instruction, this JR, we're about to bounce right out of the trampoline into kernel C code. And to see where we're going, JR is just like jump to a subroutine. The subroutine is pointed to by register T0. Print T0 to see where we're going. Maybe we'll print some instructions there. Okay, so these are the instructions we're about to jump to. They're in the beginning of the function called user trap. User trap is just a C function defined in trap.c. Here's user trap. Now we're about to jump from assembly code to user trap with a stack, with a kernel page table. Let me actually execute the instruction. And now I'm going to turn on displaying of C code in GDB now that we're executing C code. Okay, so now we're in a much more sane world. We're just executing C code. Should be a little bit easier to understand. And there's, we'll still spend some time reading and writing various interesting control registers, but the environment is hopefully a good deal less mysterious than it was in the trap frame. All right. All right, any questions at this point?
I have a question. Why didn't we see with the GDB what equal does? I maybe I missed it, but I think we jumped directly into the trampoline.
Ecall did jump. What ecall does is just changes the mode bit to be supervisor, and ecall sets the program counter register to be equal to the whatever the kernel happened to store in STVEC. Kernel stored this value that I just printed, 3FFF000, which is the beginning of the trampoline page. The kernel stores this number in STVEC before entering user space. So where ecall goes, that is where it sets the program counter to, is STVEC, which is the beginning of the trampoline page. Does that answer your question?
Yes, I think so.
Okay, so now we're in user trap. User trap is entered actually just like the trampoline page, and for a number of different kinds of traps. There's system calls, there's exceptions like dividing by 0 or using an unmapped virtual address, and there's device interrupts, and they all come here. And so user trap sort of saves and restores hardware state, but it also needs to look at the state, at the cause of the trap, to figure out what to do with it. And so we're going to see both things as we execute along in user trap. Let me just run stuff in user trap. Let's see. The first thing it does here is that it changes that STVEC register. It turns out that the way x86 handles traps is different depending on whether they come from user space or from the kernel. We've only been talking about what happens if a trap occurs from user space. There's a quite different sequence of events for traps that come from the kernel that occur while in the kernel. Because after all, for example, the kernel is already using the kernel page table. If a trap occurs while you're in the kernel, you already have the kernel page tables. There's a whole bunch of stuff that doesn't have to happen if the trap occurred while in the kernel. So before getting much further in the kernel code, we change STVEC to point to this kernel vec, which is the kernel trap handler, rather than the user trap handler. We need to, for various reasons, we need to figure out what process we're running. We do that by calling this myproc function. And myproc actually looks at an array indexed by the current core number, the heart ID, which you remember we put in TP. That's how myproc figures out what process is currently running. We need to save that saved user program counter. It's still sitting there in SEPC, but because one of the things that could happen while we're in the kernel is that we might switch to another process, and that other process might go into that process's user space, and that other process might make a system call which causes SEPC to be overwritten. We have to save our SEPC in some memory associated with this process, so it doesn't get overwritten. And it gets, we use this trap frame to save EPC as well as lots of other stuff. And anyway, that's what this current line of code is doing. The next thing that happens, we need to figure out why we came here. The scause, the RISC-V scause register has a different number depending on why this trap occurred. Some kind of exception or versus system call versus device interrupt. Value 8 means we're here, we took a trap because of a system call. And hopefully indeed, scause is 8. It does have 8 because we're here because of a system call. So we're going to execute this if statement. First thing is if some other process has killed this process, we don't want to continue, but that's not the case for our shell. It turns out that the RISC-V, the program counter that gets stored in SEPC is the address of the instruction that caused the trap. But when we resume, we want to resume at the next instruction after the E call. And so therefore, this code for system calls, which need to return, we add 4 to the saved user program counter so that we resume on the next instruction and don't just re-execute the E call. All right, next, turns out that xv6 enables interrupts while it's handling system calls, just so that interrupts can be served faster. Some system calls take a lot of time. Interrupts are always turned off by the RISC-V trap hardware. And so we have to explicitly turn them back on at this point. And the next thing that happens is we call this syscall function. And the job of syscall, I'll just enter it. It's defined in syscall.c. Here we are. What it does is it looks up the system call number in this big table of system calls up at the top of the page. If you remember, the shell's write function set register A7 to be the system call number, namely 16 for write. So what syscall does is it retrieves the saved A7 that was saved away in the trap frame by the trampoline code. And it uses that to index into this table of pointers to functions that implement each system call. So we're going to fish this number. I'm going to print num now. That's the saved A7. Indeed, it's 16, the same 16 that the shell originally put there. The system call code indexes into that syscalls table. We can find out what function it got out of the system call table by stepping into it. Right now we're in write. We're in syswrite. So is in sysfile.c. Syswrite is the kernel implementation of the write system call. I'm not going to go into this. It's like fairly complicated what happens from here on in the implementation of the system call. For this lecture, I'm only really interested in getting into and out of the kernel. So I'm going to step over the actual implementation of the system call. One thing, an interesting thing to note is that the system calls need to find their arguments. So, remember the arguments to write were 2 and a buffer pointer and another 2. And the way that the system call code gets at them is just looking at this, looking in the trap frame. So just like we could look in the trap frame for A7, we can look for A0. And that's the first argument. We look at A1, that's that buffer pointer. We can look at A2, that's the second argument, the number of bytes to write. Okay, so the system call does its job, and then syswrite finally returns. And we're gonna watch what happens. The reason for this assignment here, the reason why we're assigning to A0 in the trap frame is that this system calls all have a return value. Like write returns the number of bytes written. And the convention for C code on the RISC-V is that return values are placed in register A0 by whatever function you're calling. And so to simulate a return value, we just stick the return value in A0 in the trap frame. And we'll see by and by that when we return to user space, this A0 slot in the trap frame is restored back into the actual A0 register, and the shell sees that A0 value as the return value from write. And if we just execute through this and print p arrow trap frame arrow A0, we'll see it as value 2. What that means is that write's return value is 2, saying that it actually wrote 2 bytes, just as instructed. Okay, at this point, we're back in trap.c in user trap, just after the call to syscall. So we're now at this p arrow, which is checking if the process has been killed, because we don't want to resume executing if it's already been killed. But of course, our shell has not been killed. Skip over this, and then user trap calls a separate function, user trap ret, in order to set up all the stuff that I talked about previously whenever I said, well, before entering user space, the kernel does blah, blah, blah. It's user trap ret that's responsible for setting all that stuff up. And so we can look at all the different things it does. It turns interrupts off, but they were turned on for the duration of a system call. They're turned off now because we're about to change the STVEC to point to the user trap handler, whereas while we were in the kernel, it was pointing to the kernel trap handler. So we turn off interrupts because once we changed STVEC to point to the user trap handler, we're still executing in the kernel. And if an interrupt should occur, then it would go to the user trap handler, even though we're executing in the kernel. And for various detailed reasons, that would cause the kernel to malfunction. So we turn off interrupts, and they're left off from between the time from the very next line where we set up the STVEC to point to the trampoline, all the way through the final SRED instruction that returns to user space. It turns out that SRED instruction at the end of the trampoline turns interrupts back on. So the interrupts are on when we're executing in user code, even though we just turned them off. The next couple of lines fill in those trap frame slots that we saw before that hold various values that are convenient for the trampoline code. So the code here stashes away a pointer to the kernel page table in the trap frame. It stashes away a pointer to this process's kernel stack. It stashes away in the trap frame a pointer to the user trap function, which is what the trampoline code jumped to at the very end. And it stashes away the current core number read from the TP register so that the trampoline code can just restore that same value because user code may have disturbed it.
We have
All
a
right, then.
question.
Yes.
Why didn't we save the SEPC in the trampoline?
It could have. Yeah. I mean, the SCPC could have been, the trampoline code happens not to save it along with the other registers. We perfectly well could modify the XV6 to save it. I mean, where it is actually saved, as you probably remember, is just happened to save it in user trap in C code instead of in assembly code in the trampoline code. I can't think of a good reason to do it one way or the other. The user registers really have to be saved in the assembly code because any C code is entitled to, for all we know, the compiler generates code which modifies any user register. So those user registers are pretty important to save them in assembly code before entering C. But the EPC could have been saved earlier or later. Okay, so we're in user trap ret, sort of preparing the trap. We prepared the trap frame with all these values that are going to be needed next time there's a transition from user space to kernel, next trap. There's a couple of things we have to set up in the STATUS control register. It turns out this SPP bit in STATUS controls the mode that SRET returns to. And by clearing it, we're just saying, well, look, next time we execute SRET, we want to go to user mode instead of supervisor mode. And this SPIE bit controls whether interrupts will be enabled after we execute SRET and after we get into user space. And we do want them to be enabled, so we're going to set that SPIE bit. And then we're going to write this new modified SStatus into the actual hardware SStatus register. It turns out what SRET does, the SRET we're going to execute right at the end of the trampoline code. What that SRET does is sets the program counter equal to the SEPC register. So we're now going to set up the SEPC register to have the saved user program counter, which, if you recall, we recently saved in the trap frame. That's what's happening here. If you remember also, the trap frame contain a pointer to the kernel page table because the trampoline needs to switch to it. We need to cook up the special bit pattern that you need to write to SATP. That's done here. And I'm sorry, we're now preparing a pointer to the user page table, which we need to switch to on the way into user space. We're actually going to do that switch in assembly code because it has to happen in the trampoline, because only code in the trampoline is mapped in both user and kernel space. So we can only really switch page tables when we're executing in the trampoline, but we're not executing in the trampoline yet. We're still just in an ordinary C function. So we prepare this pointer, and we're going to pass it to the assembly code as the second argument in A1. What this line here is doing is just calculating the address of where we want to jump to at the end of the trampoline code. And it turns out there's where we want to go is user ret. User ret's the address of the instructions that'll take us back to user space. And this little formula works out the address and the sort of virtual address in the trampoline that corresponds to that user ret function. Oops. Okay, so we calculate the address of that user ret function, and then this next line uses this fn variable as a function pointer and jumps to that function with these two arguments in A0 and A1. We can now just go to trampoline code. In the trampoline code, there's, well, first we switch to the user page table. So we may as well actually execute this and then we can see the page tables change. Just for chuckles, we're still using the giant kernel page table. I'm going to run through user trapret quickly until we get to the point where it jumps to the trampoline. Oh, all right, we're in the trampoline. These are the instructions that we're about to start executing the trampoline code. They're right here. We can now, again, we'll just print the page table. It's still the kernel page table. The first thing that's going to happen here, though, is that the trampoline code is going to load that pointer to the user page table into the SATP register. So we switch page tables. If I type infomap now, we now have a much smaller user page table, but luckily still with the trampoline page mapped so we don't crash on the next instruction. The next thing that happens is this, I showed you a while ago that the second to last thing that this sequence of code does on the way to user space is swaps scratch with A0. So we need to set up scratch with the saved user A0 so that when we do that swap, A0 will end up having the saved user A0. It turns out A0 is a pointer to the trap frame because the C code passed that as the first argument. 112 of A0 is the address of the saved A0 in the trap frame. So we're going to load that and then into T0 and then load that into scratch. And at this point, we're still running with the kernel stuff in all the registers. The next 32 instructions, though, load out of the trap frame, which A0 points to, load all of the saved user registers out of the trap frame into the actual register. So we're like really close to being able to the point where we can run user code. I'm going to skip over all these loads. Any questions before we approach closer to user space?
I have one quick question. Is the value in the trap frame A0 now the return value of that system call that we made?
Yeah, the real A0 holds just this pointer to the trap frame, but after we execute the, okay, the current location of the user's saved, yes, I was calling it the user saved A0, but in fact, the system call return stuff overrode it with the return value that we want the shell to see an A0. So the current location of that A0, which we overwrote with 2 as the return value, is S scratch. So I'm going to point S scratch and hope that it's equal to 2. It is equal to 2. Does that answer your question?
Yes, I think so.
Okay, I'm gonna skip over all these loads that restore the saved user values out of the trap frame into the registers. Why don't I print out the registers at this point? Actually, I'm gonna print out the registers. I don't know if these look familiar, but they happen to be the same set of user registers we saw way back at the beginning of this exercise. For example, A1, or the stack pointer, holds this small value appropriate for a user stack low in memory. A1 is that buffer pointer that we passed to write. 2 is that number of bytes. A0, however, is the exception. It is not a saved user value because it still has the pointer to our trap frame in it. But let's look what we're about to execute. What we're about to execute is this CSR RWA0 scratch right at the end of trampoline, just before returning to user space. This is going to swap A0 and scratch. Scratch indeed has S scratch has 2, which is going to be the return value. A0 has this kernel pointer in it that points to the trap frame. But after executing the CSRRW instruction to swap them, hopefully we'll see that A0 holds this return value of 2, and S scratch holds a pointer to the trap frame, which is the second to last page in memory. And that value is going to stay in S scratch until the user program does another trap. And at that point, the trap handling code that we talked about before will be able to use S scratch to get the trap frame. All right, we're still in the kernel, but this is our last instruction in the kernel. And when I execute this SRET, it will switch to user mode. Before I do that, let's look at, it'll switch to user mode. It'll copy SEPC to the PC because we're still executing with the PC that's in the trampoline. So SRET's going to switch to user mode, copy SEPC to PC, and then resume executing. So I'm gonna run the SRET. Boom. Now we're back at address 0xDEA, which is a low address likely to be user memory, and it's the. We'll look back at sh.asm and address 0xDEA is indeed the address of the return function at the end of write. And A0 is this return value that we're supposed to be returning. So we're back in user space, and we can about to do the return back to the shell from the write system call, from the write library function that made the system call. Okay, any questions?
Sorry, can you repeat again what happens with the interrupt during SRET?
What happened with interrupts?
You said we were turning them off, but then something else turns them back on.
SRET. SRET enables interrupts. So this SRET, the very last instruction that we're executing in supervisor mode in the kernel, I forgot to say that just now, but as well as setting the program counter equal to the SEPC and switching to user mode, SRET is going to re-enable interrupts. And so that means, that's, user programs that may run for a long time, it'd be nice to be able to take disk interrupts or whatever while user programs are running.
I see, thank you.
Other questions? Okay, to wrap up, the system calls sort of look like function calls and are kind of meant to be thought of a lot like function calls, but The user kernel transitions are much more complex than function calls are. And a lot of the complexity is due to the requirement for isolation. The kernel just can't trust anything in user space. And also the desire to have simple and very fast hardware mechanisms. So really, x86 doesn't care that much about performance, but in general, operating system designers and the CPU designers are very interested in the sort of speed at which you can do the efficiency of traps. x86 does all these things in a particular way. There's certainly other ways to do them. A few questions, a few design questions, alternatives you could think about. One is can you think of ways to make the hardware or software aspects, redesign x86, redesign the RISC-V to make this whole sequence simpler? Or could you think of ways to make the whole sequence faster? And another sort of set of questions to keep in the back of your head is whether or not malicious programs could abuse any of these mechanisms to break isolation. All right, that is all I have to say for this lecture. I'm happy to take questions, though.
Sorry, I have another question.
Please.
I saw that there is a UIE register, or yeah, I think register in status, but we don't use it.
UIE.
We just use SIE and we set it to false in user space. Why couldn't we use the UIE?
UIE, gosh. The answer is going to be, I don't know. We are SP. What we set is SPIE. We may actually end up setting. I know nothing about UIE. I'm going to guess. Let me see. I'm going to guess that what actually happens here in this code where we're okay, so here we are in user trap route. We're setting SPIE in the S status. And I believe the SRET instruction will copy this SPIE. This is this previous, the name of this is the supervisor previous interrupt enable. I suspect SRET copies that bit into the into whatever controls interrupts in user mode, which is possibly this UIE bit and S status. How's that for a guess?
I see, thank you.